Let us begin very gently from the widest point of view. In statistics, we often imagine that reality is producing data according to some hidden mechanism. We do not fully see that mechanism. We only see its outcomes. We see measurements, responses, counts, successes and failures, heights, waiting times, errors, returns, or signals. Behind those observations, we imagine that there is some model, and inside that model there is some hidden setting, some unknown feature, some quantity that governs how the data tend to behave. Estimation is the act of using the data we observe to make an intelligent guess about that hidden setting. That is the big picture. There is a model, there is an unknown setting inside the model, and there is data. We do not know the hidden setting, so we try to estimate it from what we saw. It is worth repeating, because this really is the central atmosphere of the whole topic. We are not directly looking at the parameter itself. We are looking at the traces it leaves behind in the data. We are like someone standing outside a room, hearing sounds, and trying to infer what is happening inside. Maximum likelihood estimation is one of the most important methods ever created for doing this. And the deepest intuition behind it is surprisingly simple. It says, choose the parameter value that makes the observed data feel least surprising, or, in a slightly different wording, choose the parameter value under which the data we actually saw would feel most natural, most at home, most believable. That is the spirit of maximum likelihood estimation. Now let us slow down even further and separate two ideas that students often mix together at first, probability and likelihood. These two are closely related, but their direction of thinking is different. Probability asks a forward-looking question. If the parameter were already known, what kinds of data would be likely to appear? In other words, suppose the hidden setting of the model were fixed. Then we can ask, what observations would this model tend to produce often, and what observations would it produce rarely? Likelihood turns that viewpoint around. Likelihood asks a backward-looking question. Given the data that we actually saw, which parameter values make that observation seem more plausible? So probability starts from the parameter and looks toward possible data. Likelihood starts from the observed data and looks back toward possible parameter values. This is such an important distinction that it is worth repeating in common language. When we talk about probability, we imagine the model is already known and we ask what data would naturally come out of it. When we talk about likelihood, we imagine the data are already sitting in front of us and we ask which hidden model setting best welcomes the data. Same ingredients, different direction of thought. A helpful everyday analogy is the sound of footsteps. Suppose you are in another room and you hear someone walking down a hallway. You do not yet know who it is. Several people could be possible. Perhaps one person walks quickly and lightly. Another walks more heavily. Another has a very regular rhythm. You hear a certain pattern of steps, and now you try to guess who is walking. If you already knew who the person was, then you could ask, what sort of footsteps would that person probably produce? That is similar to probability. But if you begin with the footsteps you actually heard, and then ask which person would most naturally produce those sounds, that is similar to likelihood. The data are the footsteps. The parameter is the hidden identity, or more generally the hidden setting of the model. So maximum likelihood estimation says, among the candidate settings, choose the one that makes the footsteps you heard seem most unsurprising. This is why the method feels so natural. It formalizes a type of reasoning that people already use intuitively. We often explain observations by asking which hidden cause would make them seem most expected. Now, why is maximum likelihood estimation so central in university statistics? There are several reasons, and each of them matters. First, it is widely taught because it applies across an enormous range of models. Once you understand the principle, you can use the same style of reasoning for coin flip models, bell-shaped measurement models, count models, regression models, time series models, survival models, and many others. Second, it often gives estimators that feel very sensible. When students first encounter it, they often discover that the answer it produces is not strange or artificial. Quite often it matches a quantity they already felt should matter. The method formalizes common statistical intuition. Third, it connects to deeper theory. It is not just a convenient trick. In many situations, especially when the model is well chosen and the sample size grows, maximum likelihood estimators behave extremely well. So this method is central because it is practical, general, and theoretically powerful. Let us pause and reflect. We have said that estimation means guessing an unknown model setting from data. We have said that probability looks from parameter to data, while likelihood looks from data back to parameter. And we have said that maximum likelihood estimation chooses the parameter value that makes the observed data feel most at home inside the model. Now let us make this more concrete through a very simple example. Imagine repeated yes or no outcome, success or failure. 1 or 0, though let us keep the language verbal and say success or failure. Perhaps these are correct answers on a quiz item, or whether a machine starts on a given day, or whether a user clicks or does not click. We imagine that each trial has the same hidden success tendency, and we want to estimate that tendency. Suppose we perform many trials and observe the pattern of outcomes. Maybe most of them are successes. Maybe only a few are successes. Our question is, what success probability best fits what we saw? Now, if the true success probability were very low, then seeing many successes would feel unusual. Not impossible, but unusual. If the true success probability were very high, then seeing many successes would feel quite natural. So the observed pattern pulls our attention towards certain parameter values and away from others. If most outcomes are successes, then a higher success probability seems more believable. If most outcomes are failures, then a low success probability seems more believable. And if the outcomes are mixed in some balanced way, then an intermediate value seems more believable. Maximum likelihood estimation takes this simple intuition and sharpens it. It says, choose the success probability under which the exact pattern we saw is most plausible. What kind of answer emerges? Very naturally, the chosen estimate is the observed success rate itself. If about 70% of the trials were successes, then the most believable success probability is around 70%. If about 20% were successes, then the most believable probability is around 20%. This feels almost unavoidable once it is said slowly enough. Why would we choose a success probability much lower than the actual observed proportion of success, when that would make our data look oddly rich in successes? And why would we choose a success probability much higher than the observed proportion, when that would make our data look oddly poor in successes? The observed proportion is the point where the model and the data seem to meet naturally. This is a lovely example because it shows that maximum likelihood estimation is not some mysterious ritual. It is a disciplined way of saying, match the hidden tendency to the pattern that actually appeared. It is worth repeating. In the repeated success or failure setting, maximum likelihood estimation chooses the success tendency that best agrees with the frequency of success we actually observed. The data are speaking, and the estimate is the model setting that listens most faithfully. Now let us move to another famous example, one involving bell-shaped data. Imagine that we observe a collection of measurements that seem to form a cloud around some central value. The values fluctuate. They are not all identical. Some lie below the center, some above it, and the overall pattern looks roughly symmetric, with most observations near the middle and few farther out. In such a setting, two hidden features often matter. One is the center, meaning where the bell shape is placed. The other is the spread, meaning how wide or narrow the bell should be. We now ask the same maximum likelihood question. Where should we place the center so that the observed data look most natural? The answer, intuitively, is that the center should be placed where the cloud of observations balances. It should sit in the middle of the data. If we place the center too far to the left, then too many observations lie unexpectedly to the right. If we place it too far to the right, then too many observations lie unexpectedly to the left. The most natural location is the one that lets the observations gather around it with the least strain. And that natural location is the average. Again, this is not a coincidence. The average emerges because it is the point that best centers the data in this bell-shaped setting. Maximum likelihood estimation recovers it by asking where the data would look most at home. This is deeply satisfying. A quantity that students already know well, the average turns out to arise from a broad principle of plausibility. Now what about the spread? If the bell is too narrow, then observations that lie somewhat far from the center look uncomfortably surprising. The model becomes too rigid, too concentrated, too unwilling to allow the amount of variation that the data actually display. But if the bell is too wide, then the data look oddly over-dispersed in the other direction. The model becomes too forgiving. It spreads its mass too thinly and no longer reflects the visible clustering of the observations. So the estimated spread is chosen to match the actual width of the observed cloud. Once again, maximum likelihood estimation tunes the hidden model settings so that the data do not seem awkward inside the model. The center is chosen to match where the data sit. The spread is chosen to match how widely the data scatter. Let us pause and gather the thread. In the yes or no example, the estimate of success tendency matches the observed rate of success. In the bell-shaped example, the estimate of center matches the average, and the estimate of spread matches the observed variability. In both cases, the same principle is operating. Choose the parameter value that makes the observed data most believable. This is why maximum likelihood estimation is so elegant. Very different problems are solved by the same underlying idea. Now, as models become larger, one practical issue appears. When we have many observations, the overall plausibility of the full dataset is built by combining many small contributions, one from each observation or each piece of the data pattern. In raw form, this often means multiplying many numbers together. That can become awkward. So statisticians often work with something called the log likelihood. Let us introduce this softly and without making it feel technical. The point is not that we are changing the principle. We are not. We are only changing the bookkeeping. Instead of comparing plausibilities in a multiplicative form, we transform them into an additive form. In plain language, rather than thinking of many little plausibility factors being multiplied together, we think of many little plausibility contributions being added up after a transformation. Why is that helpful? Because addition is easier to reason with than repeated multiplication, especially when there are many observations. It becomes easier to compare candidate parameter values and easier to understand how each observation contributes to the overall fit. So the log likelihood is not a different idea. It is the same likelihood principle written in a more manageable language. It is worth repeating this, because students sometimes think the log likelihood is some advanced separate object. It is not a new philosophy. It is simply a cleaner way to keep track of evidence from the data. It takes a messy product of many small plausibility pieces and turns it into a sum that is easier to compare and analyze. The heart remains unchanged, which parameter value makes the observed data most at home. Now let us say something philosophically important. Maximum likelihood estimation does not ask what is morally true, or metaphysically true, or eternally true. It asks something narrower and more statistical. It asks, within the model we have chosen, which parameter value best explains what we observed. This matters because the answer depends on the model family we started with. If our model is well chosen, the method can be extremely effective. But if our model is a poor description of reality, then even the best fitting parameter inside that poor model may still not describe the world especially well. So maximum likelihood estimation is powerful, but it is always conditional on the model framework. The method is not saying, this is the ultimate truth about the universe. It is saying, among the settings allowed by this model, this one makes the observed data look most natural. That is a humbler and more precise statement. Let us pause and reflect again. By now we have built several layers of intuition. Estimation is about hidden settings. Likelihood reverses the usual direction of probability. Maximum likelihood estimation chooses the setting under which the data seem least surprising. In simple models, it gives beautifully natural answers. And in more complicated models, the log likelihood helps us compare candidate settings more comfortably. Now let us speak about why this method is so admired. One strength is flexibility. The same principle can be used in many different statistical environments. Once you understand how likelihood thinks, you can carry that style of reasoning from one model to another. Another strength is that maximum likelihood estimators often improve as more data arrive. With limited data, uncertainty is unavoidable. But as the sample grows, the data tend to reveal the hidden setting more clearly, and maximum likelihood estimators often settle near the truth when the model is correct. There is also a sense in which they are often efficient. That word has a technical meaning in statistics, but intuitively it means that the method often uses the available information very well. It does not waste the evidence in the data. Under good conditions, it can estimate with impressive precision. So the method is central not merely because tradition says so, but because it earns its importance through broad usefulness and strong behavior. Still, it is worth repeating that no statistical method is magical. Maximum likelihood estimation has limitations too. One limitation is sensitivity to model assumptions. If the chosen model family is badly mismatched to reality, then the estimate may be misleading. The method will still find the best fitting parameter within that family, but best within the family may not mean good in an absolute sense. A second limitation is that small samples can be awkward. When only a little data are available, the likelihood surface can behave in unstable or unintuitive ways. The estimate may jump around more than we would like. It may be biased. It may reflect accidental quirks of the sample. A third limitation is computational difficulty. In simple examples, the answer can be found almost by inspection. But in large or complicated models, actually finding the maximum can be hard. One may need numerical procedures, approximations, or careful optimization methods. So the idea is simple, but applying it can range from easy to very demanding depending on the model. This balance is important to keep in mind. Maximum likelihood estimation is both elegant and practical, but not effortless and not infallible. Now let us turn very gently toward Fisher information. This can sound intimidating when first heard, but the core intuition is quite calm. Some datasets tell us a lot about the parameter, and some tell us only a little. Some models are such that tiny changes in the parameter make the observed data much more or much less plausible. In those cases, the data sharply distinguish between nearby parameter values. Other models are flatter in this sense. Small changes in the parameter hardly affect plausibility at all. Nearby parameter values all explain the data almost equally well. Then the data do not pin the parameter down very clearly. Fisher information is, at heart, a way of expressing how strongly the data can localize the parameter. If slight changes in the parameter create noticeable changes in plausibility, then the data are informative. If plausibility barely changes, then the data are less informative. So one may think of Fisher information as a kind of sharpness of the model's response to parameter change. This is only an introduction, but it already conveys the atmosphere. Some experiments, some models, some kinds of data are simply better at revealing the hidden setting than others. Maximum likelihood estimation works inside that informational landscape. When the landscape is sharp, the estimate is pinned down more firmly. When the landscape is flat, greater uncertainty remains. It is worth repeating. Likelihood tells us which parameter values welcome the data more warmly. Fisher information tells us how clearly the data distinguish between nearby welcomes. One is about fit. The other is about how sharply fit changes as the parameter moves. Now let us return to the main intuition one more time, but in a slower, more unifying way. Imagine you have built a statistical model as a kind of home for possible data. The model has adjustable settings. If the settings are poor, the observed data look uncomfortable in that home. They sit awkwardly. They feel too extreme, too clustered, too unbalanced, too variable, or not variable enough. As you adjust the settings, the home changes shape. Some settings make the data feel more natural inside it. The center lines are better. The width matches better. The frequency of successes feels more reasonable. The overall observation stops looking strange. Maximum likelihood estimation is the act of tuning the model until the data look most at home. That image is often more memorable than any technical definition. It is not about proving a model true in some ultimate sense. It is about choosing the parameter setting that gives the observed data the most natural place to live. Let us pause and reflect. If a listener has drifted a little and is now returning, this is the moment to re-enter. The whole story can be recovered from a few sentences. We observe data, but the parameter is hidden. Probability asks what data would likely appear if the parameter were known. Likelihood asks which parameter values make the observed data appear most believable. Maximum likelihood estimation chooses the value that best explains the data within the model. In simple repeated success or failure data, this leads to the observed success rate. In bell-shaped data, it leads naturally to centering at the average and choosing a spread that matches the cloud. The log likelihood is just a common way to add many plausibility contributions. The method is powerful, flexible, and often very effective, though it depends on the model and can be imperfect in small samples or complex problems. And Fisher information gives a first sense of how sharply the data can identify the parameter. Now, as we come toward the end, let us let the idea settle into one final unified picture. Statistics is often the art of reasoning backward from observations to hidden structure. We do not get to see the mechanism directly. We hear the footsteps. We see the traces. We record the outcomes. Then we ask which hidden setting would make these traces feel least surprising. That is the quiet brilliance of maximum likelihood estimation. It takes a very human form of inference, the search for the most natural explanation, and turns it into a systematic method. It works across many models because the underlying question is always the same. Which parameter value best receives the data we have? Which setting makes this particular sample look understandable, unsurprising, and at home? It is worth repeating one last time that the method does not promise perfect truth. It promises something more careful. It gives the best fitting parameter within the chosen model. When the model is sensible and the sample is informative, this can be remarkably powerful. When the model is poor or the sample is thin, caution is needed. Still, the central idea remains deeply compelling. Tune the hidden setting until the observed data stop looking awkward. Tune the success tendency until the pattern of successes and failures makes sense. Tune the center until the cloud of observations bounces naturally around it. Tune the spread until the width of the model matches the width of the data. And when many observations contribute small pieces of plausibility, gather them in a cleaner additive form through the log likelihood so the comparison becomes easier to carry out. Everything returns to the same principle. Maximum likelihood estimation is the search for the model setting under which the data feel most expected. Or, in an even softer phrasing, it is the search for the parameter value that makes what we saw feel least strange. That is the unifying summary. And so we end where we began, with estimation as the attempt to infer a hidden setting from visible outcomes. Among the many possible ways to do that, maximum likelihood estimation stands out because it is natural, general, and conceptually beautiful. It asks a simple question again and again, across the whole of statistics. Given the data that are now in front of us, which choice of parameter lets them rest most comfortably inside the model? That question is the heart of maximum likelihood estimation. And once that heart is understood, many technical details that come later begin to feel less like separate machinery and more like variations on a single common idea.